In today's lesson, we're going to continue the beginning of our journey into vectors. Vectors is still a very new topic for all of you guys. So let's, as we always do, let's take a deep breath before we get started. All right, so let's see what we can learn about vectors in sort of through an algebraic lens. So in our last session, we sort of learned about how to think about vectors graphically or kind of geometrically. And today we're going to be sort of learning ways to represent them numerically and then to manipulate them algebraically. So to be able to work with them with numbers as opposed to just sort of pictures and diagrams. But in order to make sense of that, we need one really quick definition, and then we'll be able to sort of meet some very special vectors, so special in fact that they have names, and we'll be able to use those to look at all of this stuff numerically and algebraically. So that definition is the definition of a unit vector, and it's really a simple definition. A unit vector is nothing more than a vector whose length is 1 unit. So any vector in any direction that is only 1 unit long is called a unit vector. Now, at some point later in the future, we'll find out how to find the length of a vector. But for now, I just need you to know that a unit vector is just any vector that has a length of 1 unit. Now, since we live in a world that has 3 very clear physical dimensions, a lot of the vectors work that we're going to do is going to be in 3 dimensions. And so these 3 special unit vectors that I mentioned are effectively one of them for each of the directions. So there is this unit vector called I, that is generally considered to be in the x direction, a unit vector called j, that's generally in the y direction, and a unit vector called k, that's generally in the z direction. Together, those 3 vectors form what's called a vector basis for 3-dimensional space. If you study more advanced vector geometry in a field of math called linear algebra, you'll learn more about this. In short, a vector basis is really just a set of vectors that you could use to make up any other vector in that 3-dimensional space that you're in. So again, I'm not going to get into a lot of detail on that right now, but basically a vector basis is saying that these 3 vectors are enough to talk about anything in 3-dimensional space. In this next example, I hope to sort of bridge the gap between, the last lesson we had about vectors geometrically and then this lesson, which is about looking at them algebraically. So I'm asking here for us to just sketch diagrams of these vectors. Right, so we mentioned that the I vector is a unit vector, 1 unit long in the x direction. So you could kind of imagine that if you had, like a little graph here, that the I vector would be something like that. Right, it's 1 unit long. It's strictly in the x direction. It's sort of moving horizontally. So yay, there it is. If you're feeling up to it, these shouldn't be super difficult. I'm going to attempt to sketch diagrams of these other ones. So the j vector, same deal. It's 1 unit, but this time it's in the y direction. So this is what j would look like. 3i, let's see here, so 3i, remember we talked last lesson about when you put a number in front of something, it's really just scaling it to be longer. So 3i just means imagine going in the x direction, not 1 unit, but now 3 units. This would be 3i, and this thing came all the way over to 3. Okay, negative 2j. All right, well, negative 2j, that just means I'm going to take the j vector, which is in the y direction, and I'm going to scale it negative 2. So I'm going to flip it around in the other direction and make it twice as long. So this vector should be going down 2 units. This is negative 2j. All right, this is down at 2. And then in this last one, there's sort of this idea, and remember, again, we talked about this last time geometrically, that this one over here is really asking us to go 3i and then add on the negative 2j vector. So we can sort of imagine that here. If we went 3i and then went 2j, I'd wind up down here. And so we can sort of imagine that this 3i minus 2j would look something like this. This would be 3i minus 2j. You guys may be seeing some parallels between this graphing work that we just did up here and something you guys have done before in math. We're going to hold on to that thought for just a moment. And I do want to ask this question. Why would it be challenging for us to accurately sketch this vector, 3i plus 2j minus 3k? And pause the video for a moment and sort of collect your thoughts there. And really the reason ought to be because this is a vector that's in 3-dimensional space. I hesitate to call it a three-dimensional vector because all vectors are really kind of one-dimensional. They're like, it's a line, right? But this vector needs to be represented in three-dimensional space. It's difficult for us to sort of imagine, going 3 in the x direction and then 2 in the y direction and then -3 in the z direction, like through your computer screen, through your tablet or whatever you're working with. Like, it's difficult for us to do that without using some other strange things. I'm not saying it's impossible, but it is challenging. So you're generally not going to be asked to sketch those things accurately. You would just sort of draw them in two-dimensional space and label it. I mentioned on the previous slide that those graphs that we were doing, those vectors, probably reminded us of something. And that thought is going to lead us to the idea of a different notation system that we can use to represent vectors. So when we draw something like the vector 3i minus 2j, so 3i plus 2j, so 3i plus 2j would be like this. This would be 3i plus 2j. What does that remind you of? Right? Hopefully that reminds you of the idea that, hey, like, isn't the point 3 comma 2 also like over 3 and up 2? There's this sense, like, it feels like the idea of a point and a vector are really similar to one another. I'm going to talk about the difference between points and vectors later in the lesson. For now, I just kind of want us to recognize that they are similar to one another, and we're going to use that similarity. So the connection between vectors that you can represent using these ijk basis vectors and points leads us to the idea that vectors could also be written in a column vector notation, right? So, where previously we might have called something ai plus bj plus ck, we can now write that by just taking the components a, b, and c and writing them as a column. So a tall thing, A, B, C. And you can either use square brackets or you can use, sort of parentheses things. You might wonder why we write it vertically instead of like this. And really the main reason is that if I write it like this, it looks too much like a point. And I've mentioned that points and vectors are different. Again, I'll get to that later. But for now, know that you can either write things in this ijk notation or in column vector notation. And these letters, these values that we have here, are called the components of the vector. Okay. Personally, I really prefer to write things in column vector form. Almost any time I do a vectors problem, I do in column vector form. But you need to know that both of them are valid. And so on the IB exam or elsewhere, you need to be comfortable working with ijk notation or column vector notation. So just be aware of that. So everything we've said so far has really been set up. We're now going to sort of start getting into some operations and doing some things with numbers like I promised. So in our previous lesson, we learned the geometric interpretation of addition, subtraction, and scalar multiplication. Now we get to carry out those same operations using column vectors or in that ijk form. And so I'm going to do this really, really quickly. If you are adding or subtracting vectors, it's really, really simple. All you do is you add the corresponding components or subtract the corresponding components. So in this case, we have two vectors in 3 dimensions. One of them is 3, 4, -1. The other is 5, -6, 3. And so if somebody asked you to take this vector and subtract off this other vector, all you would do is you would subtract the individual components. So 3 minus 5 is -2. 4 minus -6 is +2. And -1 minus 3 is -4. And you're done. Like, you've subtracted vectors. So as long as you're given two vectors and they have components, you can add and subtract them. And this vector has the same sort of subtraction meaning that we had geometrically. And again, we'll sort of look at that in a little bit to see that connection. The scalar multiple of vectors. We learned geometrically that means that we scale a vector by some factor. And algebraically, we can accomplish this by just multiplying each of the components by that scalar multiple. So in this case, if I wanted to take this vector and scale it by -4, in other words, make it 4 times as long and point in the exact opposite direction, all I really need to do is take this -4 and apply it by multiplication to each of the 3 components. So this would become -12, 4, -28. So working with these algebraic properties of vectors is in a lot of ways very, very intuitive. When you need to add two vectors, you just add the individual components. When you need to multiply a vector by a scalar, you're just going to multiply that scalar, that number, to each of the components. Now, I want to remind you that everything we're learning in this lesson builds on what we learned in the last lesson when we were doing this geometrically. It's really important that you remember that everything we learned about the geometric interpretations is still totally valid, and often we need to blend those two things together. So let's go and take a look at this example. Suppose I ask you to consider the points M, N, P, and Q such that these three vectors are the relationship between those points. Okay? Now, you might be wondering, like, how do you draw a diagram of points that are in three-dimensional space? And I think what I would encourage you to do is just don't worry about scale at all. Just go, okay, here's M, here's N, here's P, and here's Q. Maybe that's not their real relationship, but this at least lets me sort of see what I'm working with here. And then we're told that Mn, the vector from M to N, is 3, -2, 6. By the way, did you notice there how I took this 3i minus 2j plus 6? And I just told myself, yep, I don't really like using ijk form. I'd really prefer to have it like this. Okay, so that's what Mn is. Then we were told that NP, let's see here, so N over to P, this one is the vector 1, 1, -3. And then finally, we were told that MQ, so from this one over to this one, that one is, so that one's interesting. It has a J and a K, but not an I, so we would put 0, -2, 5. And that's our, now we've got vectors for these things. Okay, so I'm going to go ahead and do sort of MP with you guys, and then I'll give you guys some space to work on the other ones. So MP, right? How would I get from M to P? And I want you to try and think about what we did in the previous lesson, right? If I wanted to get from M to P, couldn't I just follow the path from M to N and then use the path from N to P? Like basically MP should be Mn plus NP. But I have vectors for those things. Mn was just 3, -2, 6. And NP was 1, 1, -3. And so when I add those things together, I wind up here with 4, -1, 3. And so great, I found the vector for MP. So go ahead, but like pause the video, try finding B and C, vector PM and vector PQ on your own, and then we'll check in together and make sure that we've got this. So the easiest way for us to get vector PM is probably by recognizing that it's just the opposite of vector MP, which we just found in the previous problem. So, I mean, this would just be -4, 1, -3. You could also have done this one by doing, PN plus NM and sort of like oppositing these two vectors, but if you already knew how to opposite, you might as well just opposite the MP. All right, so what about PQ? If I want to get from P to Q, it looks like I'll need to go, well, that's actually interesting. We just did PM, right? So we could go from P to M and then go from M to Q, right? It kind of takes that IB idea where we use previous ideas. So PM plus MQ. PM we just found was -4, 1, -3. And MQ, we were given MQ, that's right over here. MQ was 0, -2, 5. And so when I add those things up, -4, -1, 2. And that's our answer for part C. So I hope what you really got from this one was that by drawing pictures, we can see sort of geometric relationships and pathways for how to get between points, and then take those understandings of how to add the vectors and use this idea of using components to literally add those numbers together to find, numerical representations for those vectors. So now I want to come back to something that I alluded to earlier in the video. Since they seem so similar, it can be tempting to think that vectors and points are the same thing. And really, like, what's the difference between this point and this vector? And I mean, the difference is that this is a point. It literally locates a space, like a point in space, whereas this thing represents a displacement, right? A point, and I know it's hard to sort of draw these things in three-dimensional space, but if you imagine that we had, like an x-axis and a y-axis and a z-axis, the point 3, 4, 5 would be like a point, like this point in space, right? Whereas the vector 3, negative 4, 5 is a representation of movement in that direction for that distance. So I get that they're close to one another. The difference is that this one is locked into a specific point, and this one is saying the idea of moving this far in one direction, this far in another direction, and this far in another direction. Fortunately, there is something in mathematics that can help us to bridge this gap, though. There is this thing called the position vector of a point. Okay, and all it is it's a vector that goes from the origin to a point P. It's most commonly notated OP, or sometimes just lowercase p. So for instance, this point that we had up here, if we had said that the point C was 3, negative 4, 5, you could say that the position vector for C, which is called OC, would be the vector 3, negative 4, 5. And so this is sort of our way of saying, of recognizing, we get that the point and the vector are different, and so we use point notation for C, and the position vector for C would be written using the same components, but written in a vector form. So this locates the point. This is the idea of what movement it would take to get from the origin to that point. All right, so let's see if we can put some of that knowledge about position vectors to use here. So as an example, let's consider the points A and B, okay? So part A of this thing, right? Write down the position vectors for A and B. So hopefully you saw from the previous slide that writing down position vectors for points is really easy. The position vector for A, we would notate OA, and it would be the vector 5, negative 1, 3. Similarly, the position vector for B would just be the vector negative 1, 0, 7. I'm just taking these points in this notation and writing them in vector notation. Now part B, I want us to draw a diagram of OA and OB, and then use it to find an expression for AB in terms of OA and OB. So go ahead and pause the video, try part B of this on your own, and remember that your diagram doesn't need to be like 3D and to scale. You're allowed to just say, here's A, here's O, here's B. So give it a try. All right, so if this is vector OA and this is vector OB, and someone wanted me to get an expression for AB, I would probably say, well, AB would just be, let's see here, I could do AO and then add OB. So I could do AO and add OB. Well, but OA is just the opposite, AO is just the opposite of OA. And if I really wanted to make this pretty, then I suppose I could just say that AB is OB minus OA, which means that I could do that, right? Right, AB is a column vector, so OB was negative 1, 0, 7, minus OA was 5, negative 1, 3, and so if we subtract those, we wind up with negative 6, 1, 4. Okay? And you'll notice a little further down on your notes page there that this relationship right here, AB equals OB minus OA, is a really, really, really important relationship. Many vector problems start out with that. So it's really important that you guys know that and that you memorize it. So this part right here was the answer to part B. This I accidentally got ahead of myself. This is part C for this problem. Part D asked us to find the position vector for the midpoint of AB. So I would encourage you guys now to sort of think, how could you figure out what the midpoint of this thing is? How would you get to there from the origin? How would you get a position vector for that midpoint? So again, pause the video, try that one. So for part D, I'm thinking if I wanted to get there, I would probably go from O to A, and then I would just use half of that AB vector that I used. So we know that the vector OA is 5, -1, 3. And then we want half of AB, which we just found out over here was -6, 1, 4. So that means I could do 5, -1, 3, plus -3, 1/2, 2. And then in the end, this is 2, -1/2, and this was a 2 down here, so 5. And that's our answer for part D. That's the position vector of that midpoint. Now there is kind of one more sneaky thing that I could say about that midpoint that we just found, and you can add this to your notes if you'd like. So we just noted that the midpoint of AB we found by doing OA plus 1/2 of AB. But remember that AB was just OB minus OA. And so if we actually multiply this out a little bit, you'll have OA plus 1/2 OB minus 1/2 OA. Well, wait a minute. If I have a full OA over here and I'm subtracting off of 1/2 of an, don't I together here just have 1/2 of an OA? So you can just say that that midpoint is 1/2 of OA plus 1/2 of OB. And this is another sort of cool fact that you can memorize to remember. If you ever want to find the midpoint of a vector, you can just add together half of each of the components. So if you'd like to add that to the bottom of your notes, you can. All right, so I've got one last problem for us to go through here, one last example. Part A of this is asking us to find the position vector of E. And they say that E is the midpoint of the line segment BC. Well, but we just kind of talked about that, right? In the previous problem, we talked about if you want to find the position vector of a midpoint, we can just do 1/2 of OB plus 1/2 of OC. That was kind of what we learned right at the end of that last one. But we know the position vector for B, it's right here. And we know the position vector for C, it's right here. So we could just do 1/2 of the B position vector plus 1/2 of the C position vector, 7, 8, -3. And if I put these things together, I'm going to save us a little bit of space here. This is 5 halves and 7 halves together. That would be 12 halves, so that's 6. Here I'm going to have 1/2 of 0 is 0, and 1/2 of 8 is 4. So when I add those together, I get 4. And finally, I've got 1/2 of 3 and 1/2 of -3. When I add those up there, so those are just going those are opposites, so that turns into 0. So that's OE. Okay. Now part B is asking us to show that this thing is a parallelogram. And so I really want to start here with the idea of drawing a diagram, right? So they want me to show that ABED is a parallelogram. So I'm going to start here by saying, all right, so ABED. And notice that when I did that, I sort of went around this diagram in a circle. So please don't do ABED. You have to go around all in one direction. Okay, so here it is. And I would like to give you guys the strategy for how we'll find this to be a parallelogram, and then allow you to carry it out on your own. If this is a parallelogram, then the AB vector should be equal to the DE vector. AB should be equal to DE. And then there should be one other pair of vectors that are the same as one another. And what's the other pair of vectors that should be the same? Shouldn't it also be true that AD is equal to BE? Right? Because here's the thing. If these vectors are equal to one another, then they have the same direction and they have the same length, which means that they're parallel and they have the same length. And if we have both of these things, we have a parallelogram. So I would encourage you to pause the video, make sure that you can figure out and remember how to find these things. It should be a really simple application of something we did before, and then after that we'll be done. All right, so let's see here. If I want to find AB, I know that I need to do OB minus OA, right? So I need to do the B vector, 5, 0, 3, minus the A vector, which was 3, negative 1, 1. Okay? And so if I subtract these, I'm going to wind up with 2, 1, 2. Now let's find out, is that the same thing as DE? Well, for DE, I will need to do OE minus OD. Well, we found in part A that E was 640, and D was given in the problem as 4, 3, negative 2. Well, if I subtract those things component-wise, the 6 minus the 4 is 2, the 4 minus the 3 is 1, and the 0 minus the negative 2 is 2. So yay, that one worked out. Those two things are equal vectors. Now let's try the other ones, right? We'll find AD by doing OD minus OA. So let's hear OD for us is 4, 3, negative 2, and OA was 3, negative 1, 1. I have to check and see, is that equal to OE minus OB, which is 5, 0, 3. And let's just check those real quick. If we subtract these, this one is 1, 4, negative 3. Is that equal to 1, 4, negative 3? Yep. And at the end of the problem, we might write something about why we know that these things are parallel, or rather, why this is a parallelogram. That's the end of the lesson for today. We've got a lot more to learn about vectors, and at this point, we've sort of set the groundwork for the operations that we're going to work with. So we're going to practice those a little bit longer, and then we will get into the really exciting stuff. So best of luck as you work through these problems, and make sure to let me know if you have any questions.